Okay, so this is the Unit 2A handout. And so this unit, we're going to switch gears a lot of the time here to doing stuff called proofs. And so proofs work, the way that they work is you try to explain why something's true. And every time you give a new step in your reasoning, in your logic, you have to give a reason why that works, why you're allowed to do it. So we're just going to jump right in and do a proof. And then I'll kind of go back and forth between this and another handout and show you how you can come up with different reasons for the statements you make. So the first proof we're going to do is this thing about vertical angles. And so vertical angles, I'll kind of draw on the side here. Vertical angles are angles that look like these, right? You've got an X shape and they're on opposite sides of the X. So these two are vertical angles. Those two are marked in red. If I wanted to do these two in blue, those would be vertical angles. And it turns out, and a lot of you already know this, they're the same size. So like if this was 89 degrees, this would have to be 89 degrees over here. Okay? So another way of saying that they're the same size and the same shape is saying that they're congruent. Okay, and it says right here, vertical angles are congruent, meaning they have the same size and same shape. The way to show two angles are congruent is to show that they have the same measure, that they're the same number of degrees. So our goal is to show that M1 equals M3, 1 and 3 being here. We're going to take those vertical angles and somehow prove that they have to be the same size. Okay. So usually in a proof, you're given some information and then you have to get to the final thing. You have to try and prove that. So typically what you start with in a proof is what you're given. Angle 1 and angle 3 are vertical angles. By the way, you'll discover I abbreviate all the time on these proofs. Okay, and the reason that we know that is because we were told it. It's given. So I'm going to write here, the reason we know it is because it's given. Okay. Now, by the way, I don't expect you guys to come up with something like this on your own yet, right? This is going to be not intuitive at first, but over time, you'll get better and better at it. Okay, so somehow I have to come up with some equations that link 1 to 3. So let's start, we could do 1 and 2, or 1 and 4, it doesn't really matter. But if I look at 1 and 2, you ought to be able to tell, here's 1, here's 2, that together they form a straight angle. So they have to add up to 180. So over here I'm going to say, well, measure of angle 1 plus measure of angle 2 equals 180 degrees. You can leave the degrees off if you want. Okay. Well, why is that true, right? And hopefully you remember, well, if you have two angles next to each other and you add them together, you get the big angle. And in this case, the big angle is 180. That's the angle addition postulate. Angle addition postulate. And if you wanted to, you could say this one's the special case with the straight angle. Okay. So I've got an equation that has 1 in it somehow. By the way, we're aiming for this, 1 equals 3. So I'm going to put that in the last step here, 1 equals 3. Because if we don't get there, then we haven't actually proven what we want to prove. Somehow we take the steps before it and end up with this one. Okay, so we know 1 plus 2 equals 180. Somehow I need an equation that involves 3, right? Because 3 is part of my final conclusion here. Well, you could say 4 and 3 add up to 180, but actually I'm going to choose 2 and 3 right here add up to 180, because then I've got two equations that both have the angle 2 in it. Right, so I'm going to say angle 2 plus angle 3 adds up to 180. Right, and if you needed to see it, here's 2, here's 3, and together they form a straight angle. So that's also the special case of the angle addition postulate. So the next thing we could do is say, well, notice right here that this equals 180 and this equals 180. So if I wanted to, I could replace either 180 with one of these boxes. So what I'm going to do is I'm going to substitute in, instead of writing 180 in line 2, I'm going to replace it with the green box because that's also 180. So then my next line could say 1 plus 2, that's the red box, equals, and then instead of 180, I'm going to write what's inside the green box, 2 plus 3. Okay, and the reason that we can do that is, well, they're both 180. So that's actually substitution. You're just substituting in the green box for 180. Substitution. Okay. Now, if you look at line 4, most people can kind of tell, well, I'm going to want to cancel out those 2's there. And then you'll be left with 1 equals 3. Now, the way that you do it in the proof is we're going to subtract angle 2 from both sides. But before you actually subtract it, you line it up right below. Right? You say, well, the 2, and the reason you do this is you're saying to whoever's reading this, the 2 I'm going to subtract right here is the same size as the 2 I'm going to subtract from the other side. So the left 2 and the right 2, I'm going to get rid of them. So first I'm going to show, look, here they are. I'm lining them up right below. So that anytime you set up something that equals itself, you know, AB equals AB, or angle 1 is congruent to angle 1, stuff like that, that's always called reflexive. So that's a new reason right here. This is new. Okay. And then the way to actually get rid of them, right, if you look at line 4 and you subtract line 5 from it, then you're left with line 6. Right? And you can kind of think of it like this. Right? The 2's will cancel on both sides, and you're left with M1 equals M3. So this is subtraction. Now, M1 equals M3, the measurement of 1 equals the measurement of 3. That's the same thing as saying, so the angles, angle 1 and angle 3, are the same size and shape. And the new term for that is they're congruent. So what we've proven is if you have vertical angles, then they have to be congruent. Okay. All right. So this part right here, these reasons, there are a whole bunch of them that we're going to end up using in this unit. And so what I've done is I've actually created a handout for you guys, and I've hopefully given it to you already in class. Oops, where's the thing here? And your handout looks like this. So it's all of the reasons that you could use in Unit 2. So we've already used and given. If you scroll down a bit, we've used an angle addition postulate. You guys are already familiar with the segment addition postulate. Let's see. So what I want to do is talk a little bit about how this works. Okay. So the way to read these things is if in a proof, somewhere along the line, you end up with a statement that says M is the midpoint of something. M is the midpoint right here. Then the next, and you don't know why. Maybe it's given, maybe you proved it somehow based on some other part of the proof that came before it. But what you can then say is AM has to be the same as NB, which you can either say the lengths are the same number, like 4 and 4, or you can say that the 2 segments are the same size and the same shape. They're congruent. And the reason that you can say that, if M's the midpoint, right, you can say this side here equals that side there, because it's the definition of a midpoint. That's what a midpoint does. It means one side equals the other side. Okay, it also works in reverse. If somehow in a proof you had this line, AM equals MB, then you could say, well, then M's got to be the midpoint. And the same reason applies, definition of midpoint. Notice that these are just kind of reverses of each other, right? They're actually called converses of each other. And anything that's a definition works one way and in reverse. Okay. So that's the definition of midpoint. If we come down here, angle bisector works just like midpoints, right? So midpoint here, by the way, something to note, definition of midpoint is related to one small segment equals the other small segment. Okay. So let's take a look at angle bisector, which is the same sort of thing as midpoint, except we're dealing with angles instead of segments. So if I said that this thing bisects the angle ABC, then you can say that, oh, these two little angles have to be the same, right? So you could either say that the angles are congruent, or you could say that their degrees are equal, the measurements are the same. And the reason, so if somewhere in your proof you have BD bisects the big angle, for whatever reason, then you can follow it up with, so the two little angles have to be the same, because that's what an angle bisector does. That's definition of angle bisector. And since it's a definition, it works both ways, right? If instead you had this picture and you started out with, these angles are the same, so that's this line, the two little angles are the same, then you could conclude, oh, well, then that has to bisect it, right? And that would be because of definition of angle bisector. So this one, just like definition of midpoint, definition of angle bisector, one small angle equals the other small angle. So I want to go over another idea down here in number 4 and 5. We've got definition of midpoint, definition of angle bisector. A lot of students confuse those with these two other things, midpoint theorem and angle bisector theorem, which are related. Both of them start out the same kind of way. The midpoint definition, you could start out with M is the midpoint of AB. But if instead of saying AM is the same as MB, which would be the definition up here, definition of midpoint, you're instead saying now AM is half of the whole thing, which kind of says similar stuff, but it's technically different. Instead of saying this side equals this side, you're saying this side equals half of the whole thing. That's what the midpoint theorem tells you, right? So it's slightly different. The midpoint theorem, so I'm going to add this now. Midpoint theorem says one small segment equals half of the whole segment. Okay, that's different than one small segment equals the other small segment. And then angle bisector theorem is the same sort of deal. If you have the bisector, you could say this angle equals that angle. That would be definition of angle bisector, right? That's this one up here. Or you could say instead this angle is half of the whole angle, which is this statement right here. Right. So if you have that, where one small angle equals half of the whole angle, instead of definition of angle bisector, it's the angle bisector theorem. So the angle bisector theorem says one small angle equals half of the whole angle. So you can kind of see the theorem versions are related to each other. One small part equals half of the whole part. And the definitions are related to each other. One small part equals the other small part, whether it be segments or angles. Depends on if you're looking at a midpoint or a bisector. Okay? Down here, segment addition postulate and angle addition postulate. Those don't need specific things coming before it. You just need the picture, right? So if I say AB plus BC equals AC, that should make sense to you, right? They're all on a straight line, B's in between. So you can just write this wherever it might come in handy in a proof, right? Doesn't matter what comes before it. Same deal with angle addition postulate. If you have two angles next to each other and for some reason you want to add them to get the big angle, then you can just do it. You don't have to have any particular reasons coming beforehand. So you can just say ABD plus BDC equals the big angle, ABC, because of the angle addition postulate. Or you could do the special case, you know, when they happen to end up being 180 there. So that's the special case. You don't have to write special case, by the way, if you don't want to. It's just called the angle addition postulate. And so I'm only going to go up through 7 here, because if we did all of these reasons here, probably going to be more confused than you want to be. So I'm just going up through 7. And let's go back to 2A and try to work our way through the rest of this. Okay, so number 2, what's the difference between definition of midpoint and the midpoint theorem? So I'll draw a little picture here, A, B, and N in the middle. The definition tells us that one small segment equals the other small segment. And then midpoint theorem, so that's like AM equals MB. Right? But the midpoint theorem tells us something different. That tells us that one small segment, it's not equal to the other. I mean, it is equal to the other one. But what the midpoint theorem says that's different is one small segment equals half of the whole segment. Okay. So number 3, we're going to prove it. We're going to prove the midpoint theorem. Now, when you prove the midpoint theorem, you're not allowed to use it as a reason in its proof, right? You can't say the sky is blue because, oh, it's blue. You need something else that explains why it's blue. That's not a good enough reason, right? So, so you can never use a reason in the proof of so like if you're trying to prove the Pythagorean theorem, you can't say it works because of the Pythagorean theorem, right? You'd have to figure out a different way to explain why it works. So the one thing we're not allowed to use is the midpoint theorem anywhere over here. Okay, so let's start out with a given. M's the midpoint. That's the midpoint right there. M is the midpoint of segment AB. So I'm just going to write AB. And the reason is it's given. Okay, so that's the midpoint. And then the next line says, so AM equals MB. One small part equals the other small part. By the way, where it says or here, you could also write AM is congruent to MB. The equals version technically means like however long AM is, MB is the same length, whereas the congruent one means whatever AM, the stick itself looks like, it's the same size and shape as the other stick, MB. Okay, so the idea here, if M's the midpoint, then one small part equals the other small part. That's not the midpoint theorem, that's the definition of midpoint. That's why we're allowed to say it. And if you go back and you look at the reasons list, right, back up here, we started out with M is the midpoint, and then said, so one small part equals the other small part. That's definition of midpoint right here. Okay, that's how it appears. All right, if you look at the next line, it says AM plus MB equals the whole thing. Hopefully you recognize that as it's the segment addition postulate. Now the next line says substitution, and that's not necessarily clear what we're going to plug in for the statement there. But you do know what you have to end with. You have to end with what you're trying to prove. AM equals half of AB. So somehow I need an equation with AMs and ABs. And if you look at number 3, you almost have that. The only problem is you have an MB in there. But in step 2, you know, AM and MB are the same thing. So what you can do is replace the MB in step 3 with AM because it's the same thing as MB from step 2. So this line here is going to turn into AM, that's this AM, plus, and then instead of MB, I'm going to substitute in AM because step 2 says I'm allowed to, equals, and then here's AB. Now, I'm going to simplify this a little bit. That's 2 AMs equals AB. That's a substitution, right? I'm using step 2 to substitute in for step 3. Now, if you look at step 5, how do we get from step 4 to step 5? Well, I had 2 AM equaled AB. And if you divide both sides by 2, you get this step. So this is division, right? Just divide. I'll write here as notes, line 4 divided by 2 equaled line 5. Okay, so now we've actually proven if you have a midpoint, then one small part equals half of the whole thing. Now I realize that should be totally obvious in general, but this is, I'm just kind of working through the proofs with you so you see how they're structured. Okay. Let's see what's next here. All right. So at number 4, the way that this is structured, it's kind of like mini proofs here. They're all essentially one-step or two-step proofs. And in the problem, we've got the diagram, and they give you some info. They give you that E is the midpoint of AB, and EH bisects angle BET. So I'm going to write this on the side here. Given this, that could show up in a proof as one of your first steps. Right? You've got your statements here and reasons here. And one of the statements could be E is the midpoint of AB. And that's given. And then there are some choices for what could come next in the proof, right? So let's go back to our reasons and see, when you have a midpoint as a given, what could come next? So let's come over here. Let me get rid of some of this junk. Okay, so here's one. I've got a midpoint. The thing that could come next is one small part equals the other small part, or is congruent to the other small part, because of definition of midpoint. That's a possibility, right? Another one is down here. So you start with the midpoint, start with the midpoint, and then you could say, well, one small part is half of the whole part because of the midpoint theorem. Okay, so let's come back up here. So one possibility for this could be, let's see, E is the midpoint of AB. Then we could say, so AE is the same as EB. And then that would be because that's the one small part equals the other small part. That's definition of midpoint. Or we could have said one small part equals half of the whole thing. But then that would be midpoint theorem. Okay. So those are some possibilities of what could have gone here and here. Either the first chunk or the second chunk could have gone there. Those would logically follow the fact that E is the midpoint. Similarly, we've got this. Ray EH bisects BET. Right, statements, reasons. EH bisects angle BET. That would be given. So then what are some possible things that could come next? Right, well, let's go back to our reasons and find stuff that starts out with, you've got something bisecting an angle. Right, so if you come back over here, something bisecting an angle. Here's something that bisects an angle. And then it leads to one small angle equals the other small, or is congruent to the other small angle, or their measurements are equal, one or the other, doesn't matter which. And that would be because of definition of angle bisector. One small angle is the same as the other small angle. Or, if you come down a little bit more, here's another thing that starts the same way. You have an angle bisector, so one small angle is half of the whole angle. But that one's not the definition, that's the angle bisector theorem. Okay, so if we come back over here, we got a couple options for what might come next logically, right? You might have, let's see, this one, EH bisects BET right here. You might say, since this is the bisector, that one small angle equals the other small angle. So angle like BEH is congruent to angle HET. And then that one would be the definition. One small angle is the same as the other small angle. Definition of angle bisector. Or you might have the measurement of one of the angles, something like DEH. So that's one little angle, is half of the whole thing, BET. And that would be, instead of the definition, now we're using the angle bisector theorem. So this could be another thing that shows up that would logically follow. the fact that you have a bisector. Okay. So what this exercise is doing here is it's trying to get you to come up with the right reasons for these various statements. So some of them don't require any of the given info. Like if you look at AE plus EB equals AB in part A here, well, you don't need the given info to determine that. You just need the fact that it's part of the segment addition postulate, right? Two segments right next to each other, add them together, you get the big segment. That's segment addition postulate. Okay. The next one involves adding a couple of angles. Let's see, where are they? HET, this angle, plus TEA, this angle, equals HEA, this angle. Well, that's two angles next to each other. Added together to get the big angle. That's the angle addition postulate. Why is C true? Well, E is the midpoint of AB. That was given. Right, so this one, given. Okay, let's look at D. So D says HET is half of, so let's see, HET, this angle, is half of BET, this angle. Well, we know that EH bisects the big angle. So what says that the red angle here is half of the whole angle? Well, that's got this form. We have a bisector, so we have one angle is half of the big angle. That's the angle bisector theorem. Okay. E says EH bisects BET. Well, that's a given, right? That's right here. The next one says AE is congruent to EB, and we figured out earlier, since we know we have a midpoint, we can say one part equals the other part. One small part equals the other small part because of the definition of midpoint. Let's see, what does G say? AEH, so let's look at the picture here. AEH plus HEB, so this angle plus this angle adds up to 180. Well, they're two angles next to each other, added up to form the big angle. That's angle addition postulate. And in this case, it's the special case, but you don't have to write that. It's special case because of the 180. Okay, and HTEH, this angle, is the same as HEB, this angle. Remember, EH is a bisector. That's given, right? Well, the or, by the way, anytime you have measurements are equal, you could also say TEH is congruent to angle HEB. So this one refers to the degrees are the same. This one refers to the actual angles themselves are the same size and shape. So let's see, TEH goes with HEB. Well, we knew that this was a bisector. That was given. And one small angle equals the other small angle. That's this reason right here. One small angle equals the other small angle. That's definition of angle bisector. Okay, and then the last one says BE equals half of AB. Right? Well, BE is half of AB because we knew we had a midpoint right there. Right? So what if we have a midpoint, that's the given right here. What rule says you're allowed to say then one small part of the segment equals half of the whole thing? That's this kind of form. It's the midpoint theorem. Okay. Now I realize this is probably kind of confusing at first, but the more we practice it, the better you'll get at it. You just have to make sure you're trying, right? Don't just randomly write down stuff and hope you're right. Really try to think about how you're matching things up and keep coming back to this reason list. Because as you can see, the reason list gets pretty long. Okay? So you're not going to want to slack off on this. If you don't understand something, come in soon. Come in soon for help. I'm going to stop there. The next section here is actually pretty simple, but I'm going to stop there for right now. Okay.